This is Brainiac faking their reaction. They claim that this is the reaction of about 2 grams of rubidium with water. And that this is a similar amount of cesium with water. This sort of fakery really makes my blood boil. I mean, for me, I knew the second I saw this it was fake. But how? Well, there's a general rule in dealing with high energy compounds, and that's treat everything as high explosive. It's just a rule of thumb that makes it easy to keep all of your fingers. So basically, the most energy you can pack into a gram of matter is pretty much as good as it gets with high chemical explosives. A few grams of which will blow off your fingers, but not much more. Blowing up bathtubs? Really? I mean, just to throw this all into perspective, 1.5 grams of potassium reacting with water releases about half a litre of gas, and for reference, this jug holds about 3 litres. Okay, so you do the calculations, and the 2 grams of cesium that they have here would generate about 1/3 of this gas. It really doesn't matter how quickly you do it. You will never get this sort of explosion out of the adiabatic expansion out of about 1/10 of a litre of gas. That's like half a soft drink can's worth of expanding gas. You just can't blow things up with that in a bathtub. Add a few extra clues. Why does the bathtub need dual wires going into it? Detonator. Further, an estimate of the minimum size of the adiabatic explosion limits they have here would give you something on the order of half a stick of dynamite. But what's really sad here is the contrived nature of this footage.
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub. Stand back, everybody, this one's going to be bad!
2 grams of rubidium will...
2 grams of rubidium? A hand grenade? Really? And then a similar amount of cesium.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it?
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
A depth charge in a bathtub? The crazy thing is this myth about cesium being this hugely energetic monster are almost pervasive. The myth is widespread even at universities, and I can tell you that these guys are not unique in their surprise at their fizzle.
So there's 1 gram of rubidium?
Of 1 gram of rubidium reacting with water.
The rubidium is slightly more reactive than sodium. So when we did the sodium experiments, we had our safety glasses and coat on. But for rubidium, we're going to wear secondary goggles. So here's my safety goggles, which I'm going to put on top.
See that tube still. Was that it?
Don't think I needed my safety screen.
So why? Why does 7 grams of lithium reacting with water release more energy than 130 grams of cesium reacting with water? Well, firstly, atoms weigh different amounts. For instance, a cesium atom weighs about 20 times as much as a lithium atom. And seeing as atoms really don't weigh that much, in chemistry we have this term called moles, which basically means the mass of a million, billion numbers of atoms or molecules or whatever. In practice, this means that a mole of cesium contains about a million, billion atoms and weighs about 130 grams, while a mole of lithium contains a million, billion atoms and weighs about 7 grams. So the question that I'm really asking here is which gives out more energy? An average lithium metal atom reacting with water, or an average cesium metal atom reacting with water? Well, energies are state functions, and the easiest way to grasp state functions is potential energy. I mean, take 2 shelves separated by, say for instance, a meter, and put a ball on one of them. It'll take about the same amount of energy to shift that ball from one shelf to the other, essentially no matter where those shelves are on Earth. Further, the ball really doesn't care how it got to that shelf, but when it's in that state, state function, it's got a known amount of energy relative to the other state. It's the same deal with the reaction of alkali metals with water. There's where you start and where you finish, and the energy difference between the two, that's your big bada boom. So here are your 2 reactions. But there are some generic terms in both of these reactions that we can energetically ignore when we're doing the comparison of the two. So there we go, we can cancel those out. So really, the question of which produces more energy boils down to this phenomenally simple comparison. A lithium metal atom going to a solvated lithium ion compared to the same thing for cesium. Well, thermodynamic data is available for all of the components to actually calculate this, and it's broken down into 3 steps. There's the atomization of the metal, the ionization of the metal, and then the solvation of the ion. Remember, these are state functions. They don't care what path you take to get from one state to the other. Negative numbers here mean that energy is released, and positive numbers means that energy is required. Well, when we look at it, what we find is these reactions actually absorb energy. Yeah, I know these reactions put out lots of energy, but remember that we cancel out a load of energetic terms for both of these reactions, for the comparison. And those are the bits that actually transform this reaction to being exothermic. But seeing as we've actually cancelled out those terms, the part of the equations that we're comparing here are both endothermic. They require energy. So the bottom line is that lithium, it takes a lot of energy to atomize it, a lot of energy to ionize it, but you get an awful lot of that back when you dunk it into water. And for cesium, sure, it's a lot easier to atomize and a lot easier to ionize, but you get nowhere near as much energy back when you dunk your cesium into water. So after all of that, what you find energetically is that these reactions are essentially identical, with lithium being the modest winner. But bear in mind that's for 7 grams of lithium versus 130 grams of cesium. Sure, I'd like to demonstrate this, and it would be a relatively simple experiment, but sadly, 7 grams of lithium, that's dirt cheap. But cesium retails at about $100 a gram, and I'm not sure this would be the best way to spend about $13,000. I guess I could make the stuff, and that would be a lot cheaper, but you'd have to build a kit to do it. Okay, so gram for gram, lithium releases about 20 times as much energy as cesium, and mole for mole, they're virtually identical. So why is there this difference in reactivity? Well, like I said at the beginning, the edge of the unknown is always much closer than you think. I can give you several testable hypotheses, but bottom line is I've yet to come across a reasonable explanation as to why metals like potassium explode at near detonation speeds almost on contact with water. But alas, while this interlude has been fun, regrettably I'm almost out of time. Just after the 4th of July I officially become a vagrant of no fixed abode. Don't get me wrong, I'm actually looking forward to it. I start a new job later this year, but until then I have a new metal skin under the big sky. And yeah, all of the slow motion footage acquired at the cost of molten potassium sprayed high-speed cameras was done with donations to this channel. And so I'm dedicating this video to the 3 highest donors to this channel. And in that spirit, all of this footage is available as Creative Commons. Indeed, I've created a secondary channel called Thunderfoot CC, on which I will be depositing all of this footage for Creative Commons consumption.